Hello, welcome to my channel. Welcome to Rahandran. In this video, I'm gonna derive the LC circuit response to sinusoidal excitation. So let's get started. So if you have watched my previous videos of LC source free and LC step response, um, you are gonna know that I have derived the transient response of the LC circuit. So in this video, the transient response will stay the same. The difference will be in the uh, steady state response of the LC circuit. So we're gonna only focus on the steady state response, and the transient response will be basically the same. So in time domain analysis, we are gonna apply KVL by KVL. So this is a series LC circuit, and this is an LTI system, a linear time invariant system, where C is capacitance, L is inductance. Inductors and capacitors are linear components. That's why we can apply superposition principle. Because we can use superposition principle, we can apply KVL, KCL, and LTI system itself generates linear differential equation with constant coefficients. So if we apply KVL, we will find that L d by dt it plus 1 by c it dt equals vs sine omega t. So if we rearrange this and replace the differentiation with linear differential operator, so LD plus 1 by CD IT equals Vs sine omega t. Omega is the frequency of the input signal. So let us rearrange this. LCD square plus 1 IT equals Vs sine omega t. So LC d square plus 1 it equals Vs c d sine omega t. So d is differentiation, Vs c omega cos omega t. So we have found our linear differential equation with constant coefficient. So we already know our transient response or complementary solution, which is I transient time domain C3 cos omega nt plus C4 sine omega nt, where omega n is 1 by root over LC. This is natural undamped frequency. So if you don't understand what I have done here, how did I find the transient response, the complementary solution with arbitrary constants, you can watch my previous source free and step response for the LC circuit. I have discussed in details there. So what I'm gonna do is I'm gonna only derive the particular integral part, or only solve the particular integral part of this linear differential equation. So the particular integral part for pi, which will give us steady state response. So we are solving a differential equation. So uh, and this is a linear differential equation, and in this linear differential equation we are using, or I am using, the linear differential operator. So for particular integral um, it equals omega c vs cos omega t by lc d square plus 1. So if we just omega by c vs by lc cos omega t by d square plus 1 by lc. Different when using differential operator for particular integral, for solving particular integrals, we are gonna use formula. So we are solving an f d squared. So the denominator has the d squared term in it. So if the function x is cos 80, say by f d square, then it will become 1 by f minus a squared cos omega t, given that, given f minus a square not equal to 0. So this is the formula we're gonna apply in solving this particular integral. So by our formula, omega by L V is the magnitude Vs cos omega t by minus omega square plus, so 1 by LC is omega n square. Now 1 by L omega by omega n square minus omega square Vs cos omega t. So here at this, in this point, we are gonna define something. So here our input is a sinusoidal input. So the impedance, total impedance of the series LC circuit is, say, Z. So Z is, so we know that Z impedances are plus minus j x, where x is the reactance. So in case of pure LC circuit, R is 0, and we are left with the reactance part. So j, x is basically the algebraic summation of L and C. So uh, inductive reactance is omega L, and capacitive reactance is minus 1 by omega C. So here we have found our impedance. So where omega is the input uh, frequency, the now what we're gonna do is we're gonna use this. So if Z is this, then omega L minus 1 by omega C, this is the magnitude part, and J means 90 degrees. So impedance, the magnitude part of the impedance is omega L minus 1 by omega C. So here V is by omega, so if we just divide the omega, so L 1 by LC minus omega square L 1 by omega. We're just taking this omega in the numerator to the denominator, which will become 1 by omega and cos omega t. So this will give us Vs by this, so 1 by omega c minus omega L cos omega t, which will eventually become minus Vs by impedance, the magnitude of impedance, cos omega t. So this is the particular integral solution for the particular integral for the series LC circuit to sinusoidal response. Now if we derive the full complete response of the circuit, so this is our full complete response of the LC circuit to sinusoidal input. Now we have to find the arbitrary constants. So assume that initial current through the inductor is IO. So I at t equals 0 is initial current, which gives us C3 cos 0 plus C4 sine 0, t equals 0 minus Vs by impedance cos 0. So this will give us C3 equals IO plus Vs by Z. So we know that voltage is across the inductor, or you can also take the capacitor. So I'm taking the voltage across the inductor. So this is the relation voltage between voltage and current. So L and differentiation, d means differentiation, the differential operator. So cos omega t is minus omega n sine omega n t. So C3 omega n C4 sine omega n t minus, this will become plus V is omega by C. So we know that at Vt equals 0 there is initial voltage Vo, and this is L minus omega in C3 sine 0 plus C4 omega n. So this is cos, so cos 0 plus Vs omega by Z sine 0. So we are left with omega n C4. Thus C4 equals initial voltage by omega n L. So if we just plug the values of the arbitrary constant, it will give us initial current plus Vs, the input voltage magnitude, by impedance cos omega nt plus V initial voltage across the capacitor omega L sine omega nt minus Vs by impedance, the magnitude cos omega t. So this is the current response of the LC circuit. So if you want to find the voltage response, so Vt is 1 by C I T dt. So here, let me write this here. So initial current plus Vs by Z. So cos omega nt, the integration of cos omega nt is sine omega nt by omega n. So integration of sine omega nt is minus cos omega nt, so cos omega n t minus vo by omega n l cos omega nt, and minus vs by impedance cos omega nt. So integration of cos is sine plus sine, so sine omega n, sorry, this is just applied frequency, not the natural frequency. So forced or applied frequency but t by omega sine t vo cos omega nt. So minus, there's also minus s z c. So after integration, we found the voltage response of the circuit. The response is initial current by omega n c sine omega n t minus vo, the initial voltage across the capacitor cos omega n t, minus the input voltage magnitude by impedance um, across omega n c into sine omega t. So omega here is, we have to be careful that omega here is the forced frequency or the input frequency, and omega n is natural frequency, natural undamped frequency of the LC circuit or the LTI system. So this is the complete response for the LC circuit in time domain. So I don't know if I have made some mistakes, you can check it yourself. And this is basically it. In time domain analysis, we have found our complete response, the current response is this, and the voltage response is this. uh, Here omega is the input frequency and omega n is the natural internal frequency of the LC circuit, and this is basically it.